Hello everyone. Thanks for watching my presentation on the generalized fraction order theory for non-local beams. So I will begin with a brief overview of the talk. I'll discuss the motivation behind studying non-local elasticity at the first place, and then I'll discuss some classical approaches to non-local elasticity, basically their key highlights and the major limitations. And then we will discuss how fractional calculus as a tool can be leveraged to address the limitations of the existing classical approaches. We develop the fractional order approach to non-local theory, and then we use this fractional order approach to non-local elasticity to develop the fractional order Euler-Bernoulli beam theory. And then we do some parametric studies on the fractional order Euler-Bernoulli beam theory, and we'll show you the results and the major conclusions. Now, experimental investigations have shown that size-dependent effects or non-local effects are prominent in the response of several structures. Generally speaking, the importance of non-locality in micro and nanostructures has been thoroughly investigated in literature, motivated by the apparent presence of atomic interactions, van der Waals forces, and surface stresses. So micro and nanostructures, which are typically made from graphene sheets or carbon nanotubes, for example, they find very important applications in sensors, atomic devices, surface probes, and even biological implants. Now, the effect of non-locality, particularly due to atomic interactions, is not pronounced in macrostructures. So hence the analysis of non-locality in macrostructures has been rather limited. In recent times, the analysis of non-local effects in microstructures has also gathered importance and pace. So non-locality in macrostructures has been typically connected to the presence of material heterogeneity. In fact, Professor Bazant has this famous paper on size-dependent effects in concrete. And similarly, we have functionally graded materials, which find very important applications in hypersonic structures. And even non-locality has been begun to be used to analyze the softening and stiffening of aircraft panels, which lead to localized buckling. For example, in this B-52 bomber of the stiffened panel. So yeah, and very recently, Zhu and his co-workers proposed this concept of intentionally engineered non-local designs, and wherein they used long-range connections hard-coded in the geometry over here to develop non-local metastructures, and they use this non-local metastructures for broadband vibration attenuation. So to conclude, non-locality has a very important role to play in present day complex structures, and hence the analysis and proper characterization of this non-local behavior is very important in the many applications that we discussed. So in the classical approaches to non-local elasticity, the strain and stress at a given point within the non-local continuum are related by an integral convolution operator. So this integral convolution operator is basically to account for the information within the horizon of non-locality, the additional contributions within the horizon of non-locality, which is the characteristic volume beyond which there are no longer any non-local interactions. So there are two types of approaches: the strain-driven approach and the stress-driven approach. So in the strain-driven approach, the stress is expressed as a convolution of the strains over the horizon of non-locality, and in the stress-driven approach, the strain is expressed as a convolution of the over the horizon of non-locality. However, in both of these approaches, the definition for the strain is still the same as the local continuum mechanics. So to summarize, the strain displacement relation is local and the stress strain constant relation is non-local. Now, while these classical approaches to non-local elasticity have been able to address a multitude of aspects typical of non-locality, some challenges still remain. In order to achieve a positive definite potential state, total strain energy, these classical approaches to non-local elasticity require that the attenuation kernel is symmetric in nature. This requirement of symmetry limits the application of the resulting theory to several practical cases. For example, a collection of atoms, a heterogeneous collection of atoms where the non-local interactions about a certain atom is not symmetric. This can be found in example functionally graded materials, and in fact, this was also highlighted recently in a paper by Professor R.C. Batra. And the second major limitation of these approaches is that the strain-driven approach leads to a Fredholm integral of the first kind. And this equation does not have solutions. And whenever it has solutions, these solutions are not unique in nature. So these lead to inconsistent or sometimes called as paradoxical predictions for certain slender structures under different boundary conditions. The typical example is that of the cantilever beam, where we see that increasing the degree of non-locality does not lead to a significant impact on the response of the non-local beam, where we expect that there would be a significant softening with the increase in the degree of non-locality. Now, this issue was addressed by the stress-driven integral approach, but the limitation of the stress-driven integral approach stems from its numerical implementation. Till date, there has been no practical numerical implementation of the stress-driven approach, so which prevents its application to higher dimensional structures and nonlinear analysis. Now, in this study, we used fractional calculus to address these limitations. So, fractional order operators allow the differentiation and integration of any function to any real order. Several definitions exist for fractional derivatives. In this study, we use the Caputo definition because by using the Caputo definition, we recover integer order essential boundary conditions, which have a clear physical interpretation. The same cannot be said for other definitions of fractional derivatives. Now, a closer look on the definition of the Caputo derivative suggests that it consists the convolution of local information over a memory interval with the attenuation kernel. Now, the left-handed derivative captures the information which lies behind of the point, and the right-handed derivative captures information which lies ahead of the point. And the combination of these two derivatives can be used to capture the information from the entire horizon of influence. So, unlike the classical approaches to non-local elasticity, the fractional order approach to non-local elasticity is predicated on a local stress-strain constitutive relation and a fractional order strain displacement constitutive relation. So we propose that the strain consists of the fractional order derivatives of the displacement, and the stress is the same as the local continuum mechanics approach. And this fractional order derivative of the strain is, as we showed before, is a linear combination of the left-handed and the right-handed derivatives. So these factors which have been highlighted in red are used to enforce frame invariance and dimensional consistency of the formulation. Remarkably, the strain energy density which we obtain from this approach is positive definite irrespective of the nature of the kernel. And so yeah, this is the first advantage. And so we can use this fractional order model to now heterogeneous structures by making suitable changes in the elasticity tensors. And the other thing, since the potential energy, the deformation energy is always positive definite in nature, the governing equations which are derived via variational simplifications are well posed in nature and give consistent predictions, which we will also show by the numerical results. So to summarize, in the fractional order approach, the strain displacement relation is non-local in nature, and the stress constitutive relation is local in nature. Basically, we flipped this from the classical approaches. So while we discuss this more from the point of view of energy, a more detailed approach based on defining of fractional order deformation gradient tensors and using them to derive this expression for the strain can be found in this paper. Now we use the fractional order non-local theory to model non-local Euler-Bernoulli beams. We use the Euler-Bernoulli beam kinematics to derive the fractional order strain and the fractional order stress, and then by using variational principles, we obtain the governing equations. They are well posed in nature and accept a unique solution. which we have shown in this paper in IJSS. And then we simulated the fraction order governing equations via the fraction order finite element approach, which we also developed in this paper in IJSS. We observed that irrespective of the nature of the boundary conditions, we see a consistent softening effect. And by increasing the degree of non-locality, that is by reducing alpha, we see a consistent softening, or by increasing the length scale, that is increasing the size of the horizon, also we see a consistent softening. Now, the ability of the fraction order approach to achieve a finite element implementation also enabled a nonlinear analysis, unlike the stress-driven approach. Here also we observed a consistent softening with increase in the degree of non-locality. So now I can conclude my presentation by highlighting that we developed a fractional order approach to non-local elasticity, which was positive definite in nature, irrespective of the nature of the kernel, and guarantees a well-posed formulation and amenable to finite element simulations. Using this formulation, we obtain consistent softening predictions for both linear and nonlinear static analysis, irrespective of the nature of the boundary conditions. So I would conclude this by thanking my advisor, Professor Sempalotti, and to our funders, DARPA and NSF.